Thank you very much for the introduction, Hiro. Actually, this photo was not so long ago, but it was 3 kids ago, which accounts for the extreme aging. Um, so my name's Peter Wadley. I'm a Royal Society University Research Fellow and also a professor at the School of Physics and Astronomy in Nottingham. And as Hiro alluded to, long-term collaboration with both Hiro and Mainz and Prague and Dresden and many others. So I've given up putting them all on the front page, but I would like to highlight two of the people that are responsible for a lot of the data taking and processing in the results I'm going to present today. So one of them is a postdoc in our group and a Leverhulme fellow, Dr. Oliver Armin, and the other is a PhD student, Alfred Daldin. And they've done not only a huge amount of work on collecting the data, but also driving vacuum suitcases across Europe for some years now. So I'm going to talk about altermagnetism imaged and controlled down to the nanoscale, as the title says. The system that we're going to be looking at is entirely manganese telluride, which is an altermagnet. And I'm going to talk a little bit about that system, but also the measurement techniques that basically underpin all of the following results, which I'll then present. So altermagnetic manganese telluride is a fully compensated collinear antiferromagnet altermagnet with vanishingly small net moment. And I've put here just a couple of the predictions, exciting predictions and demonstrations of those effects. So one of them that really caught my eye is this magnon splitting, chiral magnon splitting. So these are both consequences of the time reversal symmetry breaking in altermagnets. And here we see just a beautiful agreement between the prediction by Libor of this chiral splitting of the magnons, and then a demonstration not too long afterwards, so the following year, using neutron studies. The one that we're going to really concentrate on, and the one that caught my eye, so of all the time reversal symmetry breaking effects, this one is right up my street because it's a technique that we use a lot. So it's circular magnetic dichroism. We'll talk a little bit about that in a minute. But together with the group of Jan Kunesh and Hariki here, they came up with a theoretical model for it, and we demonstrated that this line structure, so this circular dichroism, I'll explain in a minute, but using polarized X-rays, we were able to measure what is a very unique fingerprint of an altermagnetic circular dichroism. And we'll go into that in a bit more detail because we're going to make a lot of use of it. So one thing to say is that manganese telluride is a hexagonal crystal. We grow it on indium phosphide, and the magnetic easy axes are all in the plane of the film. So we have the C-axis up in the hexagon, and you have 3 equivalent easy axes in the basal plane of the hexagonal unit cell. So we grow it here at Nottingham. We've been growing it for a little while via molecular beam epitaxy. So our grower, Richard Campion, has been growing for a long time. But for the last couple of years, we've been growing manganese telluride on indium phosphide 111. And this is just an X-ray diffraction scan showing how nice the crystallinity is. So here we have the manganese telluride 002 peak and the indium phosphide substrate peak. There's quite a lot of information in here, so I'll try not to go too quickly. So showing the manganese telluride unit cell, and here we're showing basically 180-degree domain in the sublattices. So the same unit cell with the spins reversed 180 degrees. And in the predictions from Hariki and in the underlying symmetry, because of the time reversal symmetry breaking, when you reverse these domains, you reverse the sign of the predicted XMCD. And again, we're looking at this predicted line structure below, focusing on 2 of the absorption edges, which we'll go over in a bit more detail. But what I want to just take away from this is that the peak structure is reversed in these 2 cases. Now, this differs completely from a PT symmetric antiferromagnet, such as copper manganese arsenide, which we looked at a lot, or any that have that type of symmetry, in that using X-rays, it would be hard to distinguish these 2 domains. Whereas in the altermagnet, if we rotate our nail vector, we're now looking top down in this image. If we rotate our nail vector around the basal plane, what you can see is that this predicted XMCD changes sign every 60 degrees. So if we look in a little bit more detail at this predicted XMCD, this circular dichroism, as I said, the line shape of this circular dichroism in the Altermagnet is very distinctive. It's a very distinctive fingerprint that you don't see in other materials. Typically, if we look at the line shape below, which is the manganese telluride, but with an applied magnetic field out of the plane, what we see is a very classic ferromagnetic-like XMCD. And this is due to the fact that we're now canting the manganese telluride moments out of the plane in this case. And I want to introduce one other concept at this point, which I think we have to do quite delicately because it's easy to get misled by it or confused. This wheel that I've put in the bottom left-hand corner. So for manganese telluride, as I said, there's a vanishingly weak magnetization, but it is measurable. It does not produce this line shape. And we know that for several reasons. One is that the DFT doesn't require any magnetization. That has no effect on the origin of this signal. And the other thing is that if we apply any field at all, we immediately destroy this altermagnetic XMCD shape. So here I've put a 6 Tesla field, which is of course large, but actually the lowest fields we tried, which is 0.1 Tesla, immediately produced this line shape due to the counting moment. So the magnetization, the weak magnetization in the manganese telluride doesn't have an impact on this altermagnetic XMCD, and indeed doesn't have an impact on the imaging. So why have I put it there? The reason is that it couples to external magnetic fields and provides a really useful handle. So I'd like you to bear this effect in mind for later on. If I was to apply a field out of plane, such as I've done here, the manganese telluride itself would prefer any of these 3 black domains that favor an out of plane. They allow a weak outer plane magnetization that couples with an external field and gives us a handle for controlling the magnetic order. So we'll come back to that. So we'll take a step back and look at the technique that we're going to be using to analyze the material. So I've done for a long time now soft X-ray absorption studies, resonant soft X-ray absorption studies, and they're particularly helpful and have been particularly useful for the study of both ferromagnets and antiferromagnets prior to this. The basis is that we go to a synchrotron facility and we use monochromatic light and we target a particular transition. So for the point of view of this talk, we'll be targeting the manganese 2D to 3P transition. I beg your pardon, 2P to 3D transition. So we target these core levels and promote them into the empty D states. And this is where in manganese all of the magnetic information lies. This is a classical X-ray absorption setup. So you're coming in at grazing incidence with linearly polarized light. The polarization of the light modifies the dipole transition probabilities. In short, I don't want to get hung up too much on the details, but it gives us a contrast mechanism that depends upon the polarization of light with respect to the magnetic order. For the linearly polarized case, it acts something like a spotlight along the direction of the E field. So if we were to shine it on this hypothetical antiferromagnet below, then when our E field is parallel to the L vector, you get a different absorption than when it's perpendicular. And that difference can vary both in sign and type, but the point is that you get a contrast mechanism. So this in itself has been used a lot for non-spatially resolved studies, but what we're going to do is combine it with an electron microscope so that when these polarized X-rays hit, they eject secondary electrons, we collect them and focus them and give ourselves full field spatial information using the magnetic contrast mechanism. So it has 2 major benefits. One, it's element specific. So we know we're measuring the parameters of, say, the manganese if we choose that energy. The other is it has very high resolution. One of the trade-offs is the probing depth is not very deep because the electrons don't escape from deeper. So this was kind of a classic setup PEAM, and most of the PEAM setups in the world rely on this. Grazing incidence X-rays coming in, focusing the electrons coming out. The reason for that is that coming down with normal incidence X-rays is difficult because you have to go straight through the center of the microscope. However, max PEAM does exactly this. So they have a normal incidence beam where both our X-rays come down and we focus our electrons up. This geometry is perfect for the study of particularly these type of altermagnets, but it makes a lot of things quite convenient, and we'll talk a little bit about that later. So we're coming in at normal incidence with circularly or linearly polarized X-rays, and we're going to be using that as our contrast mechanism for looking at the altermagnet. Just to remind ourselves that as our Néel vector rotates in the plane for the altermagnet, we have this predicted circular dichroism contrast mechanism that is new. So that for classic antiferromagnets, people have only really ever used linearly polarized light in the past, which gives a contrast that is independent of the direction of the L vector, but really just maps the spin axis. And we'll have a look a little bit at an older study. So this one was done by the group of Wadley in Oxford in 2018. And the reason I've flagged this up is they're looking at hexagonal hematite, which has the same type of domain symmetry as in the manganese telluride, i.e. it's a hexagonal compound with 3 equivalent easy axes. And so this is useful to understand how previous vector mapping of antiferromagnets has been done. And I think actually calling it vector mapping is a bit of a misnomer. It's really spin axis mapping. And what you do is you come down. In the case of the Max 4 synchrotron, you can come down and vary the direction of the electric field in the plane. In the older setup, and I think what was done for this study is actually you physically rotate the sample, and that comes with a lot of problems. It's much easier to rotate the E field from a practical point of view because you avoid all of the optical problems that people struggle with, like astigmatism. Nonetheless, the physics of this contrast mechanism is that you rotate the E field, and here are 3 possible domain types in red, green, and blue. And as your electric field vector moves away from, say, the spin axis of the green, it should follow a sine 2 theta curve. So what you do is you map this entire region while rotating either the sample or the E field, and then fit each of the pixels to a sine 2 theta curve. And in doing so, you can recreate, it allows you to assign a spin axis to each of these domains. Now, we can go one better than that with the altermagnets. And this is a problem that was really difficult in the antiferromagnets. So you can choose one of these domain types, and then with respect to it, you can define the others. But you always have the inbuilt degeneracy that you cannot tell. You can tell only an axis from this. We now have a system where if we combine all of this information, so we know that we have our Néel vector, we have our predicted XMCD and measured XMCD, and we have our XMLD that is standard for an antiferromagnet. If we use the XMCD like an operator on the XMLD map, we can distinguish between these 2 180-degree opposite red regions. And we can produce a full 6-color map, which uniquely identifies all of the possible 6 domains in the altermagnet. And that's exactly what we did with the manganese telluride using PEAM. So this, you'll notice a complete similarity. We use the same color map in a way for impact to show that this is what we can get from the linear dichroism mapping. And then this map is the binary circular dichroism map. And now if we combine these two, what it leads to is we can tell which domains are pointing, which L vector is pointing in which direction in each of the spin axis domains. And this gives us a unique amount of data about not just the L vector in the domains, but it then allows you to unpick, for example, where you have vortices coming together. You can actually go in and have a look at the vorticity and whether this is a vortex, like in this case, or an anti-vortex, like in this case. So this we found extremely exciting. It's a problem that we've had in the other antiferromagnets, not being able to know exactly what is going on in terms of the direction of the Néel vector. So this is a lovely step forward in the altermagnets and gives us a lot of room. And this is just a summary of that, essentially from the Nature paper that we published at the end of last year, just showing the full process. So from the XMCD, which is the newly predicted data, combining it with the vector mapping and get it this spin axis mapping and getting the full vector map. So now we're going to go back to thinking about this figure that I showed you with the weak magnetization, or the allowed weak magnetization also is a function of the nail vector around the circle. So the next step that we did combined two of the things that we've done. Well, one of the things that we've done in the antiferromagnets before and had no idea whether it would work for the altermagnets, and then the coupling to the external field, which I mentioned briefly before. So the thing that we did with, for example, copper manganese arsenide, and also in Mainz, they did for the manganese 2 gold, both PT symmetric antiferromagnets, was to use patterning to have an effect on the anisotropy. So as we discussed before, the manganese telluride has 3 equivalent easy axes. What the patterning does to the copper manganese arsenide, and turns out it also does to the manganese telluride, is to deepen one of these easy axes. So the patterning, the edge of the patterning has an effect on the anisotropy. And in the case of the manganese telluride, this works very well up to about 1.7 microns from each edge. These are in fact 1 micron devices. And what I want to show you here, these are linear dichroism images rotating the E field round. And the reason I've circled these arms is this is where the E field is parallel and perpendicular. So we take 2 images, 1 parallel, 1 perpendicular, and they are the most easy to interpret. Otherwise, we have to do full vector mapping, and this is a bit tricky with the edges. But these bars are quite simple. They're monodomain. And the reason you see this dark contrast in the center of them, and sometimes these bubbles, this is a 180-degree domain wall. So this emphasizes perfectly the point I made that for linear dichroism, you cannot tell the difference between the 180-degree domains. This is a great example of it. So in this case, our sublattices are swapped compared to this by 180 degrees. And all we see is the domain wall where the spins rotate across that. So, okay, this is a sample that, so what we've done with the micro patterning is in effect to create a uniaxial anisotropy. So the L vector can point, it has to point along the bar, but it can point in either direction. So that's our first act of controlling the domain structure. We create a uniaxial region. And if we have a look now with the XMCD, so this is all done, I should say, in situ on the same instrument. We really just swap the polarization and the relevant energies that we measure at. This is the same device, same region, same time. So sequentially, we took the XMLD, then the XMCD. And what's really nice here is if we focus in on this 180-degree domain wall, what we see is exactly what we expect from these XMCD wheels, is that we get a complete swap of sign of the circular dichroism across every 180-degree domain wall. So you can satisfy yourself on these bars, it's easiest to see them. You see a color change across each of these. And indeed, this little bubble gives us a little dark bubble in the white. But you can also see the 180-degree domains, even on the bars where it's a little, where the angles make it a little more complicated. You see the swap in the XMCD sign. So then the next handle of control was really, in some ways, quite not the most technically advanced, but difficult to do in vacuum nonetheless. And I'll describe what we've got here. So this is the load lock of the preparation chamber of the beam. And what we've done is simply taken an empty holder and put neodymium block magnets on top and below it. Our sample is actually, our thin film is underneath here, protected by a cap, and we get the magnet very close to it, heat the sample above the ordering temperature, which is only a few tens of degrees above room temperature, and then cool down with the magnets there. This gives us approximately 0.4 Tesla perpendicular to the sample surface, which is exactly the direction we want to couple with those different domain types. What that does in conjunction with the magnetic patterning, so the bars create this uniaxial anisotropy, but now these 2 opposite directions of the nail vector couple with the field completely differently. So one of them will copy, if we have an outer plane field, for example, one direction only will couple well with that. So the entire bar becomes single domain in order to couple with the external field. And so if we summarize that, which we did in the Nature paper, in the virgin state, all of these arms are uniaxial, but they're multi-domain, as in they're split into 180-degree domains. And you see this in the XMCD, which we've colored in. So in the final domain map, you can see that our domains are split up into 180-degree domains along the bar. If we field cool with plus 0.4 Tesla, both of these arms pick the same direction. In fact, all of the opposite pairs pick the same direction. So there is a uniquely defined direction for each of those bars under a positive field cool. If we reverse the field cool, then we reverse the specific directions of all of the opposing bars. So in summary, what that gives us is the ability to control a single domain state and uniquely define the Néel vector in it. So we started playing around with this edge effect because the edge effect propagates some distance from the edge in any shape, approximately 1.7 microns in our samples. And so if we field cool in combination with the patterning, what we found was that, again, you fix exactly the L vector along the edge. So if you do something like this, you actually create a vorticity. So in the virgin state, in these top two, they tend to align. And the reason mostly it is black, white around, except for this section, is that these are 60-degree domain walls. These have to be 120. But on field cooling, you now create the Néel vector going all the way around the outside, giving you a winding number, so a total angle around the outside of 720. And the only way that can reconcile itself is to form a vortex, an anti-vortex pair in this case. So by using these small filled hexagons, you can create anti-vortex pairs, which are then pinned somewhere in the more central region of these hexagons. If we take these shapes and make them larger, the effect still only propagates the same amount. It gives more room for kind of disorder in the center. But again, on field cooling, you create an anti-vortex pair, which then have wandered quite far apart. So the next thing you can do if you want to create a single vortex, of course, is to have a winding number around the outside of only 360, which an equilateral triangle gives you. And then if we field cool these equilateral triangles, you generate a single vortex in the core of the triangle. So I'm just going to talk about a couple of bits beyond. So most of this was published in the Nature paper at the end of last year. Some of these bits now weren't. So what I wanted to show you was in single triangles, and these are a bit smaller than the ones in the Nature paper, that you can pin a single vortex straight in the middle of the triangle. And unfortunately, so I've highlighted with red the edges of the triangle because I forget that it's quite hard to pick out what's happening in these images. The darkest regions here are actually trenches right the way down to the substrate. And these triangles here are the only material in this central region. And then you have material again around the edge. So essentially the dark regions which tend to draw your eye are the least interesting. They are just the trenches down to the substrate. But if we focus on the individual triangles, and I've picked two that are basically mirror images of each other, if we field cool, which we did, these two triangles, you can decide the exact vorticity of the triangle. So for this triangle, in that field cool direction, you always generate this anti-clockwise vorticity, and for its mirror image, you generate a clockwise vorticity. Now, unfortunately, the data wasn't quite good enough for the field cool in the other direction, but I'm going to show it you anyway because it's good enough to see, but a little bit hard to model. So this is the X-ray magnetic circular dichroism. What one would expect with the opposite field cool direction is a complete change of contrast, so a flip of black and white, which you can just about see. So you have black around the edges here with the white domain walls going into the center. And in addition to that, round the edges outside the patterning, you can also see that these are black, which is a sign that the domain structure is flipped 180 degrees. And in fact, that actually brings us to the end of what I wanted to say. So I'm going to stop it there and hope that there's plenty of time for questions if people have them.